So let's start. Let's just go back. I think I can do this in a much more sort of cleaner fashion. Let's think of a sequence labeling problem. So say a part of speech tagging like problem or an OCR problem where we're not worried about segmentation, so we definitely know what the units are in time. Okay, and so let's depict, say, an output training sequence by some varying length, but some sequence of labels. And then by the edges between labels, I'm going to assume, let's just model pairwise dependence. Now, we could easily go further. We could model like larger n-gram neighborhoods than 2, but 2 is the easiest one to talk about. Okay? So we're going to try to take sequence data, and we're trying to take each piece of a sequence and then map it into a sequence label. Okay? And when we're learning this map, we're trying to learn basically pairwise potentials, which will later be used to decode. Okay? Now I'll stall a bit. I'll stall a bit more. Wow. Purdue undergrads are really small. Okay, let me continue. So we're going to look at this sequence labeling problem. Okay, and I'm going to try to actually portray this now in a matching loss setting. It's going to be pretty easy, but it's probably easier if I just draw this diagram. Okay? Okay, I'll wait another minute. I don't have a loud voice, so I just... Okay, so we want to compute sequence labels. So let's imagine we have data. Okay, so what's the data? The data, let's say we're doing OCR. The data is going to be a segmented sequence of images of handwritten digits or handwritten characters. Okay? And now here's one of my data matrices. Let me just explain what I'm going to draw here. Each row is a feature vector. Okay? So think of each row as like a single image, like an image of one character. And we made it a vector. We added edge filter, whatever features you wanted. Who cares? It's some feature vector of one image. Okay? And all I've done is I've taken one image sequence, okay, and I've stacked it in a little matrix. So I have the first image, second image, third image, fourth image, and then I'll draw a barrier. There's going to be a barrier between independent examples, right? So one example is a sequentially connected sequence of images that's like a sentence, and we want to label that sentence, okay? But then between different sentences, we'll assume it's independent, okay? And each sentence has a different length, okay? But whatever it is, I'm just going to take each sentence, chop it up into the local part, and just stack all the parts. And just keep track of where the boundaries are, okay? So the input side's pretty easy. What's going to happen on the output side? Well, let's just pretend, since we're going to just have a pairwise dependence, for each location here in the input image, I'm going to have a corresponding output location. But it's going to be a pair, so I'm going to index the first output location at 1, but connect the pair. So the first vector on the output side is an indicator. It's going to have a single 1, but it's going to indicate the pair label for the first two images. Okay? And then if I look at the second context, I'm going to get the second output vector, and that's going to indicate the next pair. Okay? And so the first indicator is going to indicate the pair label for 1, 2. And then the next row is going to indicate the pair label for 2, 3. And obviously, the 1, 2 label and the 2, 3 label have an agreement constraint, right? That they share a marginal variable 2, which means you can't have an arbitrary labeling sequence through that matrix, right? And the constraint here is really easy. So, arg. Okay. The constraint is really easy. So say we have 3 labels. We're going to get 9 pairs. If I choose 1, 2 as the first sequence label, then the first pair label, then the second pair label could be 2, 1, 2, 2, or 2, 3, but it can't be anything else. Okay? So clearly, we could look at sort of these indicators. There's a single 1 in each row. We could think of a path through that one sequence. And there's going to be legal paths. So think of a concept of legal paths through that sequence. Okay? Now, even though the whole label set is exponentially large, right, our representation is still compact. Okay? Now, the number of legal paths through that matrix is exponentially large. Okay? But we're not enumerating those paths, hopefully, and we're not explicitly representing every path. It's just implicitly represented by some constraint. Okay? Now, it's easy to expand this. If I have a sequence of images and I want to figure out the label, say, of this letter here, I could actually build a huge input context. So in fact, I use this letter L to index the location in the sequence. At a location L in the sequence, I don't have to just use the current image. I could use a neighborhood of images around it. In fact, I could use a choice of features from everything in the sequence. Right? All I need is at every location L, I have a fixed feature representation. And I move to the next location, I get the next fixed feature representation, and so on. Okay? So I'm going to stack up these feature representations on the input side. Maybe they have broader context, maybe they don't. On the output side, I just have to enforce this constraint. Okay? And now I'm just going to think of this as a matching loss scenario where I want to pick a transfer function where I'm going to have a linear, I'm just going to multiply this whole big matrix X by a weight matrix W, and I'm going to get a whole big Z hat matrix the same size as Y, and I want to come up with a nonlinear transfer of that Z hat matrix into a Y hat matrix so that Y hat is close to Y. Okay? And what do I want to do with the transfer? I want to pick a transfer function so that the Y hats it maps into are within the legal range. Okay? Well, what's a legal range? Well, each row, I'm going to say, has to be a probability vector. Now, I know in the training data it's a discrete probability distribution, but I'm going to relax and say that my transfer function can map into row-wise vectors that are probabilities, plus a constraint, right? That if I look at two adjacent row-wise probability vectors, they have a common implicit variable, and if I marginalize those two vectors, they have to agree on the marginal. So what I need is a transfer function. I just multiply this big thing by a matrix. I just get another matrix. I'm going to put that, so that's an arbitrary matrix Z hat, just a bunch of real numbers. I need a transfer function from Z hat to Y hat that satisfies all these little constraints into probability vectors that satisfy local marginalization constraints. Okay? Say we did it this way. This is a neat way to do it. Okay? This actually works. Okay? So here's a transfer function that does exactly what we want to do the way I just described it. Okay? So let's just do this with matching losses. That's maybe better. So here's the problem. I have this huge target matrix Y, okay? And then I have my pre-prediction matrix Z hat. That's just X times W for some W. And I'm trying to figure out what's a little f transfer that maps matrix to matrix the same size so that the range space satisfies those constraints. And I'll just give you the answer. Here's an answer. This actually works, okay? Now, in the multivariate case, the way we can derive transfer functions is I really need to start with a convex potential function, and then the transfer function is just going to be the gradient of that convex potential. And here, just think a little more generally. It's a gradient, but the argument's a matrix. So I mean, by the gradient of big F, I mean a matrix the same size as its argument. Okay? So here's the answer. Here's my potential function. So I'm going to take that big matrix Z hat. Oh, I forgot. OK, ignoring the boundaries, let's just say we have one sequence for the time being. OK? And then what I'm going to do is I'm going to sum down legal paths. OK? So it's just a matrix. So L is going to index row. R is going to index column. Anyway. OK? And so what I'm going to do is I'm going to sum over all legal paths. So sum over all vectors R that indicate columns. OK? So, and then R sub L is going to be the column in the Lth row. Okay? So I'm going to sum over all legal paths, and I'm just going to exponentiate the sum down the path of the pre-prediction value. Okay? So it's just, and then I'll take a log. It's a log sum exp. All right? So, it's just an offer. Well, this actually does the job. So by the way, I have an exponential of a sum down the path. That's going to be the same as a product of the exponentials, a product down the path, right? So here we're going to see the famous sum product. Okay? But it's just this transfer. What is the, this potential? This is a strictly convex function. It's just a log sum exp. Okay? What is the corresponding transfer? Well, it's just the gradient map. I'll spare you the horror. But if you actually compute the gradient map, you get this transfer function. Let me explain what the transfer function is. What it says is, let's look at the L prime R prime. So you reach into one L prime R prime location in the matrix, and you want to know what's the y hat value at L prime R prime. And the value is going to be the sum over legal paths that go through L prime R prime of the exponential. So it's the sum of the legal paths of the product of potentials that go through that entry divided by the sum over all legal paths. So it's clearly normalized. Okay? So you can just verify that this transfer function satisfies the properties I set up front. If we could go back and verify that if we took a row and we sum over all the entries, it's going to be normalized, right? And then we're going to satisfy a marginalization constraint. Okay? And I'm not going to verify that for you, but that's one way we could think of this construction. So think of it as just a matching loss. We have this complicated potential function and this complicated transfer that satisfies the range constraints. Okay? Now, this is the transfer function. We have to use this thing. So in prediction, right, I'm going to get some new block, a new matrix, X, right, and I've learned my W. That's going to create a Z hat, and I have to take that Z hat and I have to compute the Y hat. What does it take to compute the prediction? Well, I just have to compute this function. To compute this function, what do I have to do? I have to do some product of potentials underneath, and I have to do some product of potentials on top. Okay? So the structure I showed you before is just, we're exploiting the basic tree-like structure in the output space to be able to compute these an exponential sum over a product, break it up into a polytime computation. In fact, a linear computation in this simple case. Okay? So we're just using structure to simply improve the computational efficiency of our, the things we need to compute, like the transfer function or the potential function. Okay, I haven't talked about training. That's the CRF model. So it turns out this is a CRF. And I'll show you the loss in a minute. There was a question? No? Okay. So that's where this thing is coming from. So I didn't explain well where it came from, but this is actually the matching loss for this potential. And this is, with some constant or some non-interesting terms dropped, this is also the negative log likelihood of a conditional probability model. Okay? So this may be a crazy way to depict a CRF. Those of you who have seen CRFs or know them well, this is a bizarre way to maybe explain it. But I think it's a very useful way to explain it because it shows CRFs are actually just an example, another example of a transfer function that just happens to be a transfer function designed to take structure into account. Okay? So this whole idea of multivariate predictors with transfers is actually very powerful, powerful enough, in fact, to allow us to train and predict with structured output. Okay? Now I admit that was, that was a little fast, but anyway, you see the connection, right? Okay. All right, we could also do the same thing with surrogate losses. So it's the exact same setting, but instead of getting two screens, okay. But instead of a matching loss framework, we could say, oh no, we want to do hard classifications, which means all of those output labels have to be discrete, and we're only interested in 0-1 loss. But if we want to train one of these things in 0-1, it's going to be intractable. So for training, we're going to replace the 0-1 misclassification error with a surrogate. What if we replace it with a large margin surrogate? So this is a loss that looks at the max overall alternative labelings. This is basically a loss that's just trying to boost the correct label response above all the incorrect label responses plus some margin. Okay, so you could do a large margin version of this. And it really wouldn't change much. We could get some surrogate loss, piecewise linear, convex. We could try to rewrite it as, well, here it's an LP because I forgot to stick in the regularizer. But if we stick in the our happy Euclidean regularizer, it'd be a QP. Unfortunately here, it looks like if you did like max margin Markov networks initially, it looks like it's still intractable because the problem is there's an exponential number of pieces in this piecewise linear loss function that we're trying to minimize. it looks like there's an exponential number of pieces, but there's a wonderful factorization which allows us to equivalently rewrite this constrained optimization in terms of another constrained optimization. And actually, it's not even, it's a deep trick, but it's a simple trick. The trick is, instead of thinking of a constraint for every possible sequence label, which is what this is saying, go back to the max sum algorithm. Okay, so the max sum algorithm was a message passing algorithm. This first one went back and forth, and it could be re-expressed in terms of just messages. We go to the end and we compute this first message, which is the result of the computation at the end, and then we store the result of the computation before it. Each message is summarizing all of the computation in the tail of the sequence, and we're just backing it up. And each local update is efficient, okay? That's what we saw the first time. What we can actually do is treat each of these messages as a constraint. Every sort of, each message is a little vector. We can make a little variable for each entry of that vector. And we can essentially summarize the max sum search as a poly-size set of variables. And we just impose constraints on the variables so that the message variable really means it's maximized. There's an inequality constraint that ensures it's bigger than what goes ahead of it. Okay? So the max margin Markov net is a surrogate training, large margin surrogate version of this structure prediction problem where we just recode the exponential max sum search into a polynomial size max sum search by introducing new extra variables to the optimization which stand for the intermediate messages. And since there's only a linear, or a linear quadratic, a polynomial number of messages, there's only a polynomial number of extra variables and only a polynomial number of constraints. Okay. Just maybe you're not too excited. Of course, outstanding paper award at NIPS one year, right? Like this was a big deal. But now it shows you that these two technologies, essentially CRFs and max margin Markov networks, they've actually been very useful in practice, right? So in NLP, CRFs are one of the workhorse technologies there, which those of you in NLP already know. These have been powerful ideas, but I just want to point out that they're just extensions bolted on to what we've been doing already. You can interpret CRFs just as an output transformation. Okay? Actually, you can generalize these things further. I won't explain it in detail here because it will be even less fun than what I showed you already. But essentially, all you need is any sort of structure in the output space that allows tractable computation, at least of the max sum, and perhaps also of the sum product. Any sort of structure that you can exploit. It doesn't even have to be a graphical model. It could be like a context-free grammar. It could be a graph matching problem. Or if the graph, even if it's not a tree, happens to be a planar graph. There are many famous special structures for which people invent algorithms that solve problems essentially like those. And so this generalization is taken off, right? So people learn how to solve graph matching as the output problem. Right? So where the task, say, is to find a matching between objects in two scenes or something, you can re-express it as a graph matching, and you can still train, say, large margin or a CRF-like algorithm to learn how to predict how to do good matchings, right? Or to predict how to produce good sparse trees. Okay, you don't look happy with this explanation, but this is sort of the pinnacle of the output space generalizations that I'd planned to talk about. And obviously this is a very, it continues to be a very active area of research because both the problems you can now code are very interesting, but there's no end in sight to the kinds of structures for which good algorithms can be designed that may have some applications. So both on the application side and the technology development side, there's just tons of activity going on here in language and in vision, all kinds of areas. And there's no way it's been mined out. There's lots left to do there. Yeah? Yeah, they're conditional random. So think of it as a conditional MRF. Okay. So the input is just fixed. All the input does, you change the input, it just reparameterizes the MRF. Right. Yeah, but it's just an MRF. So most of all this algorithmic structure is in the output, but it's just some Markov, some random field over structures.
In this case, you impose that structure on the output.
Yeah. Yeah. Oh, darn, I almost, oh, no, sorry, it's okay. correct. You're essentially tricking. So the model, in the CRF context, you can think of the model as just putting potentials on pairs. Like is it RC versus RE? And there's a pair. And you just have some score function. And it's a parameterized score function, and you're just tricking the parameters into putting up scores that make the training data look good, right? So the RE gets boosted above the RC. Right? And so yes, a part of that is, of course, you have to make the R look good, and you have to make the E look good. So yes, one element just implicitly is going to be the individual character recognition is going to be a very salient component of it, but also the pairwise recognition is going to be just automatically built in. Unlike some of the other MKL stuff I showed you, this actually works. I mean, this is, these ideas really do matter in NLP and more so in vision. The problem in vision, of course, is that the natural field is the grid, which is the most intractable field you could ever create. And so, you start doing loopy or things there. Yeah. Okay, good. My sprint to the end. So I've got 35 minutes. So maybe I'll just take this moment to tell you that I had a grand plan, and I'm going to make 2/3 of that grand plan. So I am going to succeed at showing what I plan to show you about input generalizations and output generalizations. I've got one more topic to cover, which you can see, conditional probability models. What I'm not going to, unfortunately, be able to do is tell you about one single scrap of research I've done in my life. Which is really unfortunate. But I was sitting there last night thinking, do the right thing or do what I want to do? And anyway, I just ran out of time. So I gave a dummy slide which showed an outline of all the stuff I didn't do. But maybe I could just ask, you could just look at my website, look at papers, ask me offline. I think there's some amazingly cool projects, that are just in the pipeline right now, mostly having to do with exploiting matrix norms to tractably solve feature learning problems in contexts where we thought it was impossible or intractable. And actually, there's been some recent, extension of the kinds of matrix norms that you can exploit tractably that lead to powerful new forms of, joint dimensionality reduction, semi-supervised training, all kinds of things, jointly. Wish I could tell you about it, but maybe we'll do that offline. Okay. Question?
Yeah, could you talk about that instead?
Could I what?
Could you talk about that instead?
Yeah, I could, but that would be the wrong thing to do. Plus, I made slides for. I had to decide what am I going to make slides for, this or that. It was this. Okay, this will go quickly though, this will be easy. I won't do much in depth, but I can at least just finish off this depiction of like generalized linear modeling and tackle sort of the last major sort of issue that we haven't, or I haven't covered yet. Okay, so everything we've done up to now, I think like I mentioned in a response to a question yesterday, everything we've done up to now is just simply point predictors, right? You give me an input, I just give you an answer. That one answer, right? My optimum prediction for that input. No sense of uncertainty in that answer. That's just the prediction, okay? Many of you are, statisticians and probabilists, and you've been cringing in horror for the last 2 days, right? Because that's really a brutally simplistic way of thinking about modeling, probabilistic data, or even thinking about prediction. So I agree, okay, but you have to agree that a lot of the technologies I've been explaining are deployable, they're efficient, they're well known, they're flexible, and people can work wonders with this stuff. Okay, so what I've told you up to now isn't useless. I think it's actually incredibly powerful, but true, it's lacking in something, and I would say the major thing it's lacking in is exactly this representation of uncertainty in those predictions that we're producing. So I'll just sketch out how that still seamlessly kind of fits in. So instead of a point predictor, we'd like to do something like have a proper representation of some conditional distribution of the output given the input. So sure, we could pull the most likely output, but maybe we'd like to know more than that. Do we have to start over again? No, right? I mean, we could really look at this as a very just simple next step to extend what we've got now to incorporate a little bit more in the model, okay? Before I start extending it, just maybe some warm-up exercises. What if I even had, a conditional distribution? My client might still say, I don't care, I want you to make predictions, right? Look, I got to make a decision, okay? So, just as a warm-up exercise, you all would know things like if I have a distribution, say even a true distribution, what's the best point predictor for that distribution? And that is actually going to be highly dependent on the loss function that we've chosen. The obvious example is if our condition, for any conditional distribution, if our loss is squared prediction error, the optimum point predictor is always the conditional expectation, okay? But that's just squared loss. Like, how general is that conclusion? Well, it turns out that conclusion is extremely general. It turns out we'd reach the same conclusion for any matching loss. So any of the matching loss constructions that we've developed, softmax, exponential, any of them, if we use the corresponding Brakeman divergence or matching loss, and then we ask for, even if we had a conditional distribution, what's the optimum point predictor? The optimum point predictor, again, is the conditional expectation. So at this point, you'd be thinking like, oh, I guess it's always the conditional expectation. So maybe I can always represent a conditional model by the conditional expectation plus some fuzz. But that's clearly not true, right? So if we look at other losses, like say absolute error, we discover, I didn't really show it very well here, but we discover for absolute prediction loss, the best point predictor is the conditional median, okay? You know what this tells us, by the way, immediately? This tells us that the absolute error cannot be a matching loss. There is no transfer matching loss construction that leads to that. Oh well. Anyway, so the space of optimal point predictors would be maybe more general than conditional expectations, but since I've really been puffing up matching losses, we're probably going to be satisfied with conditional expectation. In the misclassification error setting, it's the misclassification, in terms of misclassification error, the optimum point predictor, of course, is just the maximum probability label, or the maximum probability output given the input. Okay. But now we're hoping to do something about keeping a full conditional, so we would like more than just say a conditional expectation. We'd like to keep something like, say, a variance or an entropy or some measure of uncertainty around that prediction, okay? First thing I'm going to show you is that there is a sense in which we get all of that for free without really changing anything. Now, because it's free, you get what you pay for. It's limited. But we will get a sense of conditional distribution for free with really not doing anything. And how does that come about? That's going to come about just by a very basic fundamental connection between Brakeman divergences, which are the things we've been working with, and exponential family models, which are the things that we're going to be looking at. Okay? So just to set this up a bit, the free ride comes from just reminding ourselves about some well-known, or at least now well-known, properties of Brakeman divergences and how they're related to probability models. So just a reminder. So let's go back to a simple setting. Brakeman divergence is going to have a couple of elements in play. We're going to have transfer functions, and we're going to have transfer functions on the targets and on the predictors. We'll get post-vergence, post-target, pre-target, post-prediction, pre-prediction. But these transfer functions, I didn't emphasize it too much, but let's agree to think about settings where the transfer functions are invertible. Okay? If they happen not to be invertible, it means we have like an overly rich representation. We can always map it down into an invertible setting. So if I'm going to just start assuming we have invertible transfers. So I can go from a post-prediction to a pre-prediction or a pre-prediction to a post-prediction, either way, whatever I want. Okay? I didn't emphasize this too much, but if we have a potential function, a strictly convex potential function, well, we can use this conjugate, this Fonchel conjugation operator I showed you before, and we can derive its corresponding dual potential function. Okay? Happily here, we'll get some very nice kind of explicit reductions, at least in simple cases, where I can write for a given potential function, there's going to be a conjugate potential, which also will be strictly or another convex function. Okay? But it's just on a different space. But happily, it's going to turn out that the conjugate potential is going to be on the post-prediction space, whereas the original potential is going to be on the pre-prediction space. So there's all this beautiful connected structure going on. Finally, if we have the forward transfer and its inverse, and we have the original potential and its conjugate, we're going to have all kinds of mappings between equivalent Brakeman divergences. So here's a fundamental one. There's almost even a sketch of how it works. If I have a Brakeman divergence or a loss function between a pre-prediction guess and a pre-prediction target, that's going to be equal to always, it's just a general theorem, to another Brakeman divergence defined in terms of the conjugate potential where I've reversed the order and it's now in the post-prediction target and the post-prediction guess. Anyway, just Brakeman divergence trivia, okay? This will make things a little bit easier when we connect it to probability models. So, okay, when we were doing matching losses, we actually, there's two subtle variants. We were thinking of using Brakeman divergences in this way, where we explicitly thought of like a loss between a target and then a guess, but we parameterize our training in terms of pre-predictions. So we introduced the nonlinearity right here, okay? And then we want to train this loss. Now this loss looks hard because Brakeman divergences are only convex in the first argument, but because of the duality property I just showed you, this loss is actually going to be equal to this loss, and we'll see quickly that it's guaranteed to be convex. Okay? So this is sort of the convex training in the context of a nonlinear transfer that we've been looking at. Okay? I just want a word of caution. You can actually use the same Brakeman divergence construction, but not impose a nonlinear predictor. You could still stick with linear predictors, and you still get Brakeman divergence, but you're going to have a lot of trouble maintaining convexity and so on. Anyway, you can play around with these things. I'm just going to stick to this form here that we've been developing. Okay, finally, so how do we represent a conditional model? Well, if we've picked a nonlinear transfer and then we derive, we have a potential associated with it, all the, the conjugates and the inverses, and we have a Brakeman divergence associated with it, it turns out for free, we're going to get a natural conditional distribution associated with it. Okay? And the conditional distribution is going to be an exponential family model where, given our pre-prediction value, we're going to get a conditional distribution over post-prediction values. Given by the simple exponential family, normalized. And it turns out that the potential function is going to be the normalizer of, or the log normalizer of this exponential family. Okay? So this is, again, a free connection that's understood, right? By construction, this potential function, we could have started with the conditional distribution model, and then this would be the log normalizer, which is guaranteed convex. If it's convex, it's a potential function, okay? And that potential function is going to lead to a Brakeman divergence, and that Brakeman divergence is still going to be related to the initial model. In fact, if we look at the Brakeman divergence we derive from the potential that we derive from the exponential family model, we'll find that we can rewrite the exponential family model just in terms of this derived Brakeman divergence and the conjugate potentials and so on, okay? So I'm just painting a map that connects all these things, right? It's a bit hard to read the papers on it because there's all kinds of little technicalities I'm just sweeping under the rug. But the sort of the utilitarian connection between these objects is pretty straightforward. Okay? So I can think now of, once I've picked my transfer, I've picked a loss and I've picked a conditional distribution. And in fact, I've picked a conditional distribution so that the expected value, the conditional expectation, is my post-prediction. And the optimum point, and that will be the optimum point predictor if that was the correct conditional model, and so on. Okay? So I could claim at this point that all along, all this stuff has just been there in the background. We never had to do anything. We always had a conditional distribution. It's just that the optimum point predictor, under the loss that we're assuming, is the conditional expectation, so we never had to change anything. It was the same point predictor. Okay? But if you're really hung up and you want to go back and get an entropy or variance or something over that point prediction, well, you just can dip into your exponential family model that corresponds, and there it is. Okay? It's a bit glib, but this is one sort of seamless step to show how we can get to conditional distributions without much pain. Okay? So nothing I've said is against probability modeling. I guess I'm trying to claim that everything I've said is entirely consistent with conditional probability modeling, at least in a certain way of constructing it. there are some, deep works going on here. There's this really, impressive paper in 2005 that many of you might know about that actually shows a nice bijection. If I start with an exponential family model, can I construct a proper Brakeman divergence associated with it? If I start with a Brakeman divergence, can I actually construct, an exponential family model associated with it? Do these things always exist? Are they appropriately unique? There's a really nice theorem that shows a bijection between a certain, regular class of Brakeman divergences and a certain regular class of exponential family models, and shows that they really are in a one-to-one correspondence. Yeah?
This is not true. This theorem is actually flawed. There are some cases where things don't quite work.
Yeah.
It is not clear. I mean, it is clear that the Brakeman divergences are a larger family than the exponential family, but it's not clear that the bijection exists. So there are some corner cases.
Okay. Okay, fair enough. But you know where this could go, right? Where this could go is you see this word regular here and that word regular there. You change those definitions until you get your one-to-one, and then anyway. But there's no doubt though there's this interesting relationship between these two. Well, I didn't know about that, so.
Is that theorem constructive?
Nah, I wouldn't say that. Yeah. Yep. Yep. Okay. Good. My home stretch. Okay, that's just representational stuff. Okay, I'm not claiming that's the only way you want to think about conditional distributions. Clearly not. But it is a way that's essentially been implied by the constructions I've shown you so far. So if you find that limiting, then that is a legitimate complaint about the modeling capabilities I've shown you. If you find it enabling, then that's a euphoric extension that was there for free. Okay. Next step, though, is one thing to be able to just represent these models, but then how do we train these? And now let's go back and think about training in the context of probability models instead of like these crazy loss minimization frameworks that the narrow corner of machine learning people like optimization like to do, okay? But I think you see this coming. It turns out that the relationship between standard probabilistic or criteria and loss minimization frameworks, again, winds up being essentially equivalent, okay? Until we get to Bayes, and we're getting to Bayes, okay? But let's start simple. So we start out saying, okay, forget about losses. We're interested in hardcore probability models. We have conditional models parameterized somehow by a W, okay? And then we get independent training data where we have a conditioning variable and a condition, or the other way around. We have an input and an output, okay? And we simply want to train our probability model, our legitimate conditional distribution map to maximize the conditional likelihood of the labels we saw given the input data, okay? Of course, if I plug in the representation I just showed you, we discover immediately that maximum conditional likelihood is exactly equivalent to Brakeman divergence minimization. That's what we've been doing all along. Okay? Again, if you accept this particular way of constructing a conditional model, which you may not be happy with, but if we chose that, there's nothing new here. Conditional likelihood, loss minimization, same thing. Okay? And that's a good thing, right? It's not like the, okay, anyway. You also see this step coming. The next step is like, what if we're going to start to be a little bit Bayesian and have like a prior on the parameters, right? And so we would get a graphical model or a generative model that looks sort of like this. Nature draws the parameters from some prior. And then once nature's made that decision, the data is observed independently given the choice of model. But then it's generated under some conditional distribution, okay? And now we want to do, say, maximum a posteriori estimation, which is, find the parameters that maximize not just likelihood of data, but some combination of prior and likelihood of data, which again, if you're a committed Bayesian, you would say, come on, this is still lame, okay? But, next step, and you won't be shocked to discover that if we plug in now this particular form of conditional model that I showed you, that again, this would just reduce directly to a case of loss minimization on the losses using the same models we've been using, with an extra term out here, which I'll call the regularizer, which is the minus log likelihood of the prior. And so if I pick a Gaussian prior on W, I will get squared Euclidean regularization. I pick a Laplacian prior, I'll get L1. Things will get more interesting if we go to the multivariate case and I have a matrix and I have some prior on matrices and I'd like to have prior distributions that give me trace norm or prior distributions that give me block norms. That would be more cool. I don't even know how far people have gone there. Presumably it's all been worked out. Anyway, but we know you could go the other way. I could take one here and work back to some prior. I don't know. Anyway, I'm completely agnostic. I'm just showing that these things are actually connected, right? Okay, so finally we get to the pinnacle, I guess, which is, say, a fully Bayesian perspective. And this is a good perspective. I mean, it's powerful, it's elegant. In fact, it's much more elegant than the other perspectives in a very basic sense. So here the idea is, certainly nature, we have a generative probability model. In fact, we put everything into a probability model, okay? And all of our reasoning is just inference, probabilistic inference, right? We have random variables, we have distributions on random variables, and we're just doing inference on random variables, end of story, okay? Which is perfectly fine. So here's a generative model that kind of depicts the setting we're in. We have nature generating some choice of model. Given the model, the data is conditionally independent. Now we're just doing conditional modeling here, so we're not actually modeling anything about the generative process behind the inputs. You could add that if you wish, but I would claim this is more flexible, okay? So we get our training data generated conditionally independently given nature, and then we get a test example, some new independent observation, conditioned on the model, given some output. Okay, so there's various implicit independent assumptions I'm making here. Anyway, so we get a test prediction. Okay, so the Bayesian perspective is that there is no optimization, right? If you're a real Bayesian, you never optimize, at least in a simplistic sense. You only integrate. Okay, now integration computationally is a fine problem to be working on, right? Just like optimization. Okay, so integration's fine. So what we'd be interested in here is not optimizing our model parameters. Clearly, what we're interested in is actually marginalizing out our model parameters. In fact, forget about the model parameters. What do we care about? We care about the distribution on that label given what we know. And what do we know? What we know is the training data and the test input, but we don't know the model. So if we just want to make the best inference we can about the thing we don't know given what we do know, then what we're interested in is the predictive distribution, right? That would be the conditional distribution on the output y hat given the corresponding input x, but also given the training data, because the training data actually is coupled here if w is not known. If you know the model, the test is independent of training, but if you don't know it in this model, they're coupled, okay? So we would like to be able to just compute this predictive distribution. So if you wanted to do a point predictor, you would be interested in computing the conditional expectation. If you're interested in more than a point predictor, like the full uncertainty in the prediction, then you would be computing other aspects of that conditional distribution, like variance or something. And this is good. This is perfectly fine, and there's well understood relationships of what's going on. I'll come back to the computational question shortly. But we can even decompose this predictive distribution a little bit. It's just marginalizing over the latent variable, the model parameters. And given our various independence assumptions, it breaks down into this very nice form. So I want to draw your attention to this. What this is saying is, okay, this term here is one model, right? So you've made one choice of weight, and you get your conditional distribution. So under one model, that's your conditional predictor, okay? And what we're doing is we're summing over all possible models, and we're trying to get the best prediction by summing over all models, looking at each model's prediction, but then taking a weighted average, where we're weighting the models simply by their posterior likelihood. How likely was that model given the training data? Okay? I know you've seen this before, but I feel like contractually obliged to go through. Okay? And then, of course, these posterior weighting on the model can be, again, given our independence assumptions, just sort of expanded out into, using Bayes' rule, into the prior times the likelihood normalized. And there's, I don't even need to apologize. I like Bayes. This is a great idea, okay? And so if we were interested in point predictions, for example, we could use just the same weighting to compute an optimal point predictor. If I could compute the posterior weighting, my optimum point predictor is just to take a weighted average of the predictors. And I can have my nonlinearity sitting in there because of the way I set things up, at least in this Brakeman divergence matching loss scenario. My conditional expectation is the post-prediction transfer, right? So Bayesian learning, even with these Brakeman divergence-like constructions, is still very elegant, and my optimum predictor is just a weighted average of the predictions I would have made anyway, where I'm weighting by the posterior over the model. Yeah? They change the structure based on what?
Based on what the inputs are. Here, you assume they have the same set of W's no matter what S and Y is. So you can assume that may match a different structure depending on what W is depending on the input is.
Sir, that sounded really interesting, Sergey. I hear only every second word.
I'm saying that in this case, you assume that you have the same set of W's for all sets of inputs.
Oh yeah, yeah. Okay, so you can. So this isn't like all of Bayes. I clearly, I'm in a. Well, you might think of this as parametric modeling, although I would claim that I can make things look essentially non-parametric. But yes, we're doing things like assuming that the model structure W doesn't change when you change the input-output pair, right? All of our modeling up to now has basically said we have a fixed feature. We have fixed feature representations, input, output. Now those feature representations don't have to be finite, but they're fixed, okay? And then we get this simple picture. Yeah. Yeah, well, you may like or hate this answer. The prior is completely independent of the prior is essentially playing the role that the regularizer was playing. And notice that in my discussion, I've carefully separated loss from regularizer, and I've kept them independent. So, the choice of regularizer is just based on independent thinking, I guess, from the choice of loss. So there's no coupling, yeah, which I think is good. You might think is bad. Right? Because if I have one, I still have to think about the other. But there's no coupling in the way I've been showing it.
Yeah, with the prior, you can kind of envision the regularizer is just something that moves you in the space of your solution. So, I don't know, the probability space seems to make more sense because I had a version of that or something. I don't know.
Yeah. This is the attraction and danger of Bayes, which is, seems very principled because it's modeling. It's none of this crazed machine learning, pick random features, random regularizers, twiddle knobs, get it to work. This is like you think about the phenomenon and you model the generative process by which things get generated, right? And that's good thinking. That's very good thinking. The thing to be aware of, though, is that's not the only way you can do things. And some of these crazed people who are picking random features and random regularizers, they're building amazing image retrieval systems. So I don't know what type of person you are. I'm just saying they're all those types. They're gonna, yeah, okay. But if modeling is good, okay. But let's get to the consequence, which is, we know again, the elephant in the room. Bayes is attractive, right? If you had the associated computational infrastructure that we have with all of the other loss minimization stuff I've been showing you, we wouldn't be having this presentation about all this other lame generalized linear modeling stuff. For the most part, I think, we'd mostly be talking about, modeling using Bayes, right? The problem with what I've just shown you, or the difficulty, isn't conceptual. Conceptually, it's beautiful. The real consequence of Bayes is computational, right? The computational consequences of Bayes are fairly dramatic. Now, integration problems aren't necessarily harder than optimization problems. There's hard and easy versions of both, okay? But we know that in Bayesian model averaging, just even in the simple way I'm depicting it, you can't do any of what I showed you without being able to compute these two integrals, right? You need to be able to integrate this with respect to your model space, and you need to be able to integrate this with respect to your model space. And if you can't compute those integrals, you can't do Bayes, not exactly, okay? Computationally, this is a major headache. So as all of you well know, it's pretty easy to just go back to using MCMC, right? Now, okay, first of all, I like MCMC. I've worked on MCMC, but you know what MCMC stands for, right? It stands for I give up. I have no reasonable computational strategy in mind whatsoever that's going to lead me to reasonable ways to compute these. So I'm going to reach into this black box that is guaranteed in the limit, in the heat death of the universe, to compute these integrals for me, and I'm going to trust it, okay? Actually, MCMC is a lot like global optimization because it is attractive, it's very compelling, it's interesting, but people who really go there never really come back, right? Now, this isn't Bayes' fault. I think it's the research community's fault. So, okay, just another thing I want to say about this, right? Machine learning isn't just about the modeling, right? It really is this composition of statistics and statistical modeling and thinking with computation, right? And computation is not something we ignore. I haven't ignored it at all, right? If you compose the most beautiful, intractable thing you like, but good luck, right? Everything that I've been doing so far has been trying to exploit well-developed existing technologies for optimization. And trust me, it's incredibly well-developed. The tricks, the tools, the reformulations are really paying off, and we already use them, okay? I actually think one of the main research questions I have when it comes to Bayes isn't how I can model things with Bayes, it's how I can actually do integration problems. And there you find that the existing, at least as far as I know, the existing understandings, reductions, maps, reformulations of integration problems are far behind what exists in optimization. So I think this leads to what we're seeing in the short term, which is this kind of domination in a lot of application areas of people using hard, optimization approaches when they really should be doing Bayes. But they can't just download a piece of software on the net and get reliable answers, right? So I think that this is actually a major computational question that really somebody in the machine learning side, other than Radford Neal, should be seriously picking up on, right? So it seems underdeveloped. And I think a lot of the real power of this kind of modeling is yet to be seen because it's not really practically deployable, at least naively. Okay, yeah, I'll try to hear again.
Yeah, wouldn't you encounter first the dimensionality when you try to compute the sum? You don't necessarily encounter it when you do optimization. So I'm not sure whether we will be able to succeed quite as well with integration as we did with optimization.
I heard every second word. Can you really yell?
I was saying that when you do integration, you encounter first the dimensionality, which you don't necessarily encounter when you do optimization. So I'm not entirely sure whether we will succeed quite as well in integration.
Well, cursor dimensionality? I guess, okay, cursor dimensionality in the following sense. In optimization, I get huge dimensions. And, my programs slow down, but they don't slow down exponentially because, we probably have some reasonable solver that's polynomial. Now, those polynomials aren't very pretty, necessarily, but, at least it feels tractable. Whereas here it's cursor, yeah, but I don't know. I think, look, in optimization, the first thing you learn is you never accept the problem as it's handed to you. Unless you've proved it's NP hard, what do? You start pulling out your toolkit of reformulations and you wiggle and you thrash and then you get a form. Or you convince yourself you can't do it, okay? And I don't think there's the same existing repertoire of reformulations available. Now, there are lots of relaxations and approximations like variational strategies and mixes of Monte Carlo and structured forms of Monte Carlo. It's all good stuff, but it's not the same as saying I have this problem and I have an equivalence-preserving transformation to this, equivalence-preserving transformation to something that ultimately I have a good, efficient, provable algorithm for. Wouldn't it be grand if we had that kind of existing technology? And I just feel like it's not there, and I think that's consequential. Yeah?
Is that true also in the statistical community? Outside of CS, I know optimization is, well, it's sort of in the CS family.
I guess
But, and I know a lot, at least in the department I'm from, but in statistics, is it the same, is it just that this sort of stuff hasn't been transferred over to CS, or that it just doesn't exist?
could be, I could be very naive about it, but I'm worried. Because if it existed, I think, people would really be wanting to use it. And whoever's been hiding it, you're a fool, right? You could get famous by letting people in on how to solve these. Yeah?
So as an admirer of Bayes, I got to ask this question here. So I see the correspondence between a two-level hierarchical model and the laws and generalizer-based approach.
Yeah.
I think they
Okay.
But I don't see the correspondence for higher level of hierarchy. For example, 3-level hierarchical model, 4-level.
Yeah, yeah, okay, yeah, sorry. The reason this picture looks so simple is no latent variables at all, no latent structures whatsoever, right? If we start to introduce like missing inputs or outputs, but even interpose layers of representation in the map, things get, well, look, things get bad everywhere. But even the modeling equivalences are all going to break down. Yeah, I think, that's the Wild West. Still, I think, even though a lot of us are working on it. But computationally, even now, we're just starting to make some progress on computationally tractable forms of latent, structure modeling in the context of say, generalized linear forms, for example. Just a sec, I'm just trying to see. So I got 5 minutes. I'm going to take one more question, and I'm going to try to end my lecture. One more?
So it is along the same lines that where we are talking about dimensionality, issue of depth. I think it is very specific to which domain we are talking about, like where the target label, if the target label has a particular structure within itself, which you talked in the previous slide. I think if you look at the structure, which is mathematically in there, in the target label, then I think dimensionality issue can be answered.
Maybe.
I
I see. So you think in the structured output scenario that we can break an integral like this down into a lot of lower dimensional integrals?
Yeah, because there are two ways of parameterization. I look at it. It's like parameterization.
That sounds like a great idea.
Which is like a feature space and it can be infinite. Like
Yeah.
how many features you should go for. But if you look at the problem where your output label Y is a structure, then if you parameterize that structure, then I think there is a way of dimensionality.
There might be, except maybe. I don't know. Maybe we can talk about that offline. Maybe. Yeah. Okay. So I took a big gamble. I knew people would get mad at me, but I'm just trying to explain a simple way of thinking of these things. I just wanted to finish with a tractable case that's a famous one, but maybe I shouldn't bother to teach you about Gaussian processes, but I thought Gaussian processes are a beautiful instantiation of Bayes, because we have the happy circumstance of being able to solve all the integrals we want to solve in closed form. And as you know, Gaussian processes are very powerful, essentially because given some restrictions on the output side, you're allowed to exploit all of the input generalizations that we've talked about up to now, all of the extensions to kernels. L2 regularization is the same as a Gaussian prior. Everything works out elegantly. And as a result, this is a version of Bayes that is widely deployed and does show the benefits of having an uncertainty representation in practice versus not just having point predictors. The problem with Gaussian processes, very simple, like least squares, Gaussian outputs to say nonlinear transfers. Again, we run afoul of the integration problems, and there are not a lot of existing tractable formulations, and we are back to doing variational approximations or MCMC. But anyway, if you stick literally to Gaussian modeling, maybe I'll just skip ahead, you can actually get a closed form for the predictive distribution, which happens to be a Gaussian. Of course, a Gaussian, if you're in a joint Gaussian, all conditioning and marginalization leads you to Gaussians. If you combine Gaussians in reasonable ways, you're going to stay Gaussian. So it's essentially an exercise in linear algebra to show how you can represent the predictive distribution as a Gaussian. And happily, that Gaussian allows you to easily extract the point predictor, the conditional expectation, but also the conditional variance, right? And just the toy picture that everyone sees. This is a scenario where you really do get an interesting, non-vacuous representation of uncertainty in the outputs. So this is almost like the dream of Bayes. And we would like, and it's already very powerful and widely deployed, but we'd like to be able to take this dream and still fully generalize it in the way that we can fully generalize in the non-Bayesian setting. But unfortunately, the moment we sort of walk a little bit out of the Gaussianity assumptions, we lose known, effective tractable algorithms. So again, I see from the machine learning side, this is something the computationalists, I would hope, would really be spending a lot more time on, and hopefully somebody will. I keep trying to convince, I have convinced the odd student over the years, but not many. Okay, let me just wrap up by doing one last thing. This was the third part I didn't give, but I just want to say this kind of unified perspective of things. Now, there's a danger of unification, right? Because we leave a lot of things out. There's all kinds of things that don't fit in, okay? But I'm just saying there's a lot of things that do. This kind of endeavor of having a simple, clean, way of just patching on extensions does go beyond what you've seen so far here. You can actually start to push this all the way into things like unsupervised training, and latent variable training, while maintaining the same flexibility on input representations and output transfers and Brakeman divergences and so on. This has not been fully played out yet, but it's starting to play out now, where just simple, elegant extensions like, we have a supervised problem x to y, and I take away the y labels, and you go, oh, the horror, it's a completely different problem. Well, actually, a lot of the same modeling and a lot of the same thinking, and even a lot of the same loss functions and regularizers and expansions are all applicable, with one particular strange little way of looking at things. And if those are all applicable, if you go from unsupervised to semi-supervised, you wind up with new and yet I think fairly compelling forms of semi-supervised training that treat supervised and unsupervised on an equal footing, as opposed to bolting together two independent concepts. And you can take it one step further, and you can start to think about, like, deep networks, or models where you do have latent structure, where you're learning not just a linear model, but you're learning at the same time some latent structure, perhaps imputing latent structures or marginalizing over latent structures, while jointly learning models that can recover latent structures from inputs and outputs. And some, in the optimization setting with appropriate matrix norm regularizers and so on, a lot of progress is underway right now, with like new sort of computational breakthroughs coming out and showing us how we can do simultaneous latent structure learning, dimensionality reduction, and so on. In many cases, unsupervised, like sparse coding, or supervised settings, and still do it tractably, and still do it as flexibly as this. So that's the story I guess I'll have to give the next time I do a summer school. But anyway, thank you for your attention, and I'm happy to talk to you after. We're late, so.